Hello everyone, you are watching Code with Shubhajit, and today we will be discussing one of the medium level problems from Geeks for Geeks, which is count inversions. So let's go through the problem statement and understand what's trying to say. Okay, so we are given an integer array ARR and we have to find the inversion count in the array. So what is an inversion count? Whenever we have two elements ARRI and ARRJ forming an inversion, if ARRI is greater than ARRJ and I is lesser than J. Okay, so what I can understand from here is that let's say if I take this array, right? 2, 4, 1, 3, 5. Now, the cases where any left element is greater than the right element, those are the cases which we have to find. So, in this array, what are those cases? Those are 2 and 1. 2 is greater than 1, but the index of 2 is actually lesser than index of 1. 4 is greater than 1, and then what else? We have 4 greater than 3 as well. Okay, so these are the three pairs which I'm able to find where there is an inversion is happening. Okay, so the inversion count for this array will be 3, and you can see the explanation as well. Let's go to the OneNote and understand more about the problem and also see how the logic will look like. So I have taken the same array 2, 4, 1, 3, 5, and as I have discussed that these are the 3 points: 2 with 1, 4 with 1, and 4 with 3, where the inversion count is happening. So the inversion count will be 3 in such case. Okay, I want you to understand that the most brute force approach which is coming to my mind is just traversing over this array twice using a double for loop. So it will look something like this. We will have a for loop where we will be having an I which will be going from 0 till the second last element, that is this element. I is less than n minus 1 and I plus plus. Then we have another for loop which will go from I plus 1, then j is less than n, so it will go to the last element, and then j plus plus. So these double for loop will actually traverse all such combinations. So if I give you an example, that let's say our I is at this point, in that case our j can actually traverse all these points going from 1 till 4. Okay, so whenever our I is, let's say, as 0, now j is at 1, right? J is at 1. What it will see, that is I, ARR of I, is it greater than j? No, it's not. Then inversion count doesn't happen. J points here. Is ARR of I greater than ARR of j? Yes, it is. So I will increment the count plus is equals to 1 for these cases when ARR of I is greater than ARR of j. Okay, for these cases I will, so this is an if condition. So for ARRA greater than ARRJ, count plus is equals to 1. It will happen. Okay, and this count outside I will take it as 0. That is basically the inversion count only. Okay, so now this is done. Now when, let's say, our I is here, now it gets incremented to the next value 4. Now our j will range from 2 to 4. Now when our j is at this index 2, is 4 greater than 1? Yes, again count will increment. Then j will go here. Is 4 greater than 3? Yes, again count will increment. So currently the count value is 3. Okay, now we come here. No, 4 is lesser than 5. Now whenever I points at index 2, after that 1 and j points here, right? So j can point in these two places. When j points at 3, 1 is not greater than 3, 1 is also not greater than 5. So no inversion count increment happens. And now when I is at this index 3, that is the last index which it can go. At that point, what is j? J is this index, right? This index is equals to 4. Is 3 greater than 5? No, so no inversion count increment happens. So this is the way we are actually calculating it with a double for loop, and the time complexity for this will be a big O of n square. Why? Because you are having a double for loop over the array, so that actually creates a time complexity of big O of n square. If we want to decrease the time complexity, okay, then what are we gonna do? We have to find that out. Okay, so for that there are some prerequisites which we need to understand, and I will explain you them. These prerequisites are: you have to understand how merge sort works. That is the one prerequisite which we want to understand, and in that only we will also understand how two sorted arrays are merged into a single sorted array. I have taken this array again, indexed them out. So Now I will be applying the merge sort algorithm over it, and in between I will explain you how we will be incrementing the count, which will be helpful for our count inversion logic. Okay. In merge sort, what we will do, we will actually first divide the array going so first we will divide the array into half, then the left half will go to the same algorithm again, the right half will go to the same algorithm again, and it will again make it half till the point only one element is left in the array. And once that is done, we will again build the block by merging these arrays, and they will be sorted along the way, and at the end what we get is a merged sorted array. Okay, I will explain you here with this example, so don't worry and don't fear. Okay, so here we have the left index as 0, the right index as 4. So what is the mid? So the mid here is left plus right, that is 4 plus 0 divided by 2, which is equals to 2. So the index 2 is mid here. So what I will do, I will take this part 0, 1, 2 as the left, and I will take this part 3 and 4, that is mid plus 1 to right, as right. Okay. Now what I will do, I will take them here 2, 4 and 1. Okay. This is the right array part, which is 3 and 5. Looks good, right? And now we will do the same thing again. Okay, now what is mid for this? Mid for this will be 2 plus 0 by 2, and what is that? That is 1. So, and I will also calculate the mid here. What is mid for this? 3 plus 4, that is 7. 7 by 2, which is so in Java it's not 3.5, it actually rounds it off to the nearest integer, which is lesser. So 3.5, what is the lesser integer nearest we have? That is 3. Okay, so it is 3 here, this one. Now what I will do, I will actually divide them again. So here it is 1. So from 0 till mid, that is 0 till 1, we will be having an array, and this we are having one more, that is mid plus 1 till right. Here from the left, that is 3 here till mid, that is the single element only, and here mid plus 1, that is 4 till the right. What is right? Right is 4 here only. So they will be single blocks. Okay, they will be single blocks. Here it is 2, 4, and here it is 1. Okay, looks good till now. Now as you see that we have encountered a 3, 5, right? That is single blocks. In that case, and I will also index them out, in that case what will happen, it basically means that okay, we have actually found single blocks. We will not do anything now. What count we will be returning with this whenever we have single blocks? Okay, let's not put the count thing now. I will put it later on so that you will better understand, else you will get confused now. So just the merge sort part, understand it better. Okay, so we have 3 and 5, which are single blocks. So we will just return them. So we will return 3 and we will return 5. So they come here as it is. Okay, and once these recursive calls are made, so these all are basically recursive calls to the same function. Okay, again and again we are recursively dividing this stuff. So when they are returned from these left and right recursive calls of the same function, then what will happen, we will actually merge them, and we are definitely sure that whatever coming from the left side is sorted, whatever coming from the right side is sorted, because that's how the algorithm recursively works. Okay, so the 3 which is coming from the left is sorted, for the 5 which is coming from the right is sorted. Now we have 3, 5, we will try to sort it out. And when we try to sort it out, we see, okay, we don't need any sorting because they are already sorted here, right? It's good. Now, on the left hand side, if we see, we have 2, 4 with an index of 0 and 1. Here it is 2. Okay. This needs one more division, which is mid will be 0 plus 1 by 2, which is 0, because 1 by 2 is 0.5. The nearest integer lesser is 0 only. So till mid and mid plus 1 till right. So left to mid, which is only this element, and mid plus 1 to right this element. Okay, I hope you are able to understand this. Now we have this 2 and we have this 4. Again the same scenario as we have with 3 and 5. We have these two elements which are single elements only, so we will return them as it is because they will definitely be sorted. Single elements are always sorted for any array. If there is a single element in an array, that is definitely sorted, right? So we don't go much further into that. Now we got 2 4. Is 2 4 already sorted? Yes, 2 4 is already sorted. We don't need to sort that. Okay, so now, and on the right side we have a 1 which is also a single element, so it will be also returned as it is, and this thing will also be returned as it is. So we have now from the left coming as 2 4, from the right, okay, coming as 2. So now what will happen, it will actually first sort them out and then it will write this array. So instead of going up, I will do one thing. I will make the things bottom, okay, so that things will not mess up there. So 2 and 4 coming along, they will be the same array because they are sorted. Now 1 is coming from here, 1. Now when 2, 4 and 1, they are actually merged, okay, because these two are the sorted sets. 2 and 4 is sorted, 1 is sorted. But when we try to merge them, we need to change the positions here, okay. So 1 will go before, then 2 will come, then 4 will come, okay. So we will do that once we have actually traversed the left part of the recursion and the right part of the recursion. Same thing we are gonna do here. Both of them comes, and we have 3 here, we have 5 here. They are already sorted. Good, right? So from the right portion we have 3 5, from the left portion we have 1 to 4, and it's guaranteed that 1 to 4 is sorted on its own, 3 5 is sorted on its own. So whenever it is going up and up after the recursion has happened, it is already sorted at each step. Now we have to actually merge both of them into a single sorted array. And how are we going to do that? There is a final array which we'll be taking, which is 1 2 3 4 and 5. So this is the final sorted array which we are getting, okay. Index 0 1 2 3 4. Okay, I hope you are able to understand how the merge sort algorithm is working, okay. And please give attention to it. Now I will be explaining you that how is the actual count inversion thing will come out when we are actually merging these two arrays. So if you see that when we are going to merge this 2 4 with this 1, okay, that is the left subarray with the right subarray, we can see that it's not that we are just making it 2 4 1. No, these two needs to be shuffled to find the sorted array, right? So we have to understand here that this one, okay, I am positioning, and when I am positioning, where I am positioning that, I am positioning it as the first element, that is passing 2 and 4. Before 2 and 4 I am positioning this one, okay. It means that we have 2 inversion count while doing this. We have got an inversion count of 2 while doing this, okay. Why I'm saying that, because 1 was on the right in the main array. See, 1 was on the right in the main array from 2 and 4, and when we are moving 1 to the start, we are actually passing these two elements, that is 2 and 4. It means that there are two pairs of inversion count, that is 2 1 and other one is 4 1, which has occurred here. And this is where it gets interesting, that how our inversion count will be 2 for this operation, okay. It's good. But here if you see 2 4, they were already sorted. Given if it was, let's say it was 4 2, on the left it was 4, on the right it was 2. Here if we see it was, if it was 4 2, then what will happen, one more inversion will be happening, because in the final sorted array we will be having 2 4, which is the reverse of that, because 2 comes before 4, and how many elements 2 has to surpass, it has to surpass one element. So that's why there is a pair of 4 2 in this case, okay. I just took it to explain you, okay. Just a diversion I have took, but this will not count here because it was actually 2 4, not 4 2, okay. So till now we have an inversion count of 2 from this. Now on the right also, if you see 3 and 5, they are already sorted, so there is no inversion count happening. So from 3 and 5 and from 1 2 and 4, when we do the merging again of these two sorted arrays, we have to see, okay, 1, it's fine coming to the left, 2, it's fine coming to the left, but if you see 3, when 3 comes before 4. What does it mean? 3 has to surpass one element from the left array, okay. From the left sorted array, 3 has to surpass one element. In that case, the inversion count will increment by 1, okay. So now the inversion count is 3. Why I'm saying that? Because 3 comes before 4. So we are moving an element from the right to the left, and how many elements it has surpassed to move to that position? It has surpassed one element. Given that if there was a 9 also here, then 3 would have surpassed two elements, 4 and 9. Okay, I hope you are understanding this. But that's not the scenario now, just to give you an example. And now we have 5, and 5 comes after 4. So there is no increase in inversion count because 5 comes at the last. It doesn't have to surpass any element from the left sorted array. So with this, when we are doing the merge sort, it also gives us the inversion count by applying this logic in between. Okay, I hope you are able to understand. And this was quite a bit of complex explanation, but if you see it again, if you're confused, if you see it again, you will be able to understand that. And now we will go to the code part. Okay, so this inversion count is there. Here I will actually call the recursive function for the division of the array first, and then merging and sorting that part. So that function I will be calling. Okay, so initially let me take the ARR length so I don't have to compute it again and again. And what I will be returning, I will be returning, so the count which is returned from the recursive function, and this recursive function I'm naming it as inversion count util. I will be passing the ARR to that. I will be passing the leftmost element of the array for now, which is 0. The rightmost element will be indexed as n minus 1. Okay, now I will define the inversion count util. I will take the ARR, and then I will take the left, and I will take the right index. Okay, so in case of recursion, we need to have a base case. And for us, what is the base case? If you see, I have explained it here, that whenever we have single elements in the array, right? Whenever we have single elements, in that case, we need to just return. Okay, and in this case, as we are returning the inversion count at every step, so we will be returning the inversion count at every step. So do you think for single elements there will be any inversion count? No, because they are already sorted, right? So the inversion count which will be returned, not this side is 0 only. For this, 0 only. In this case, 0. This case, the inversion count which will be returned 0. And what is the base condition? The base condition is whenever we have the left and the right pointing on the same element. Okay, whenever we have left and right pointing on the same element, then we have a base condition. Let's do that. So if left double is equals to right, okay, in that case we have the base condition coming, we have to return a 0. Okay, but if that's not the case, we have a left which is lesser than right. Okay, then we need to again divide it into left and right array. So for that we need to calculate the mid first, which will be left plus right by 2. And now we will also be having a inversion count which is 0 initially. Okay, and then what we will do, we will add it what we are getting from the left part, and we will also add it whatever we are getting from the right part, because we will be getting some inversion counts from the left side as well as from the right side, right? The left subparts and the right subparts. Okay, so here we will be calling the recursive function again with this ARR with the left, because we are now going towards the left side. So with the left, and what will be the right for me now? The right for me is mid. Okay, because I have divided it into half. Now in the second line, what I will be doing, inversion count is equals plus is equals to, now I will be going towards the right side. So for that, I'm taking the array mid plus 1 comma right. I hope you are able to understand that part. I have divided the array into two parts. One is left to mid, the other one is mid plus 1 to right. Okay, good. And from both, whatever inversion count is coming, I will be adding it to our this local variable. Once from both the sides we have got the inversion count, we are definitely sure that both the parts from the left to mid part and from the right, that is mid plus 1 to the right part, these both parts are sorted. Okay, so if they are sorted, we can actually merge these two sorted arrays, and then we can actually check that, okay, while merging them, do we have any more inversion counts happening? So that's why I will do this inversion count plus is equals to, now merge and count inversion. This is the method which I will be using here. Okay, merge and count inversion. Now what I will be sending here, I will be sending the ARR, I will send the left index, I will send the right index, and I will also send the mid part. Okay, because they don't have to recalculate mid from left and right. Why we need to recalculate, right? So when this thing is done, we can return the inversion count. But hold on, this is the main function which we need to actually implement, and let's implement that. Okay, so now what we are gonna do? Okay, so hear this part a bit with a bit attention. So we know that from left to mid it is sorted. We know from mid plus 1 to right it is sorted. Now we have to merge them. So for merging them, we first need to store the left to mid part somewhere else. We have to store the mid plus 1 to right part in some other array, and then because we will be changing the actual ARR here, okay, and when we are changing the actual ARR, then we need to store these left to mid parts and mid plus 1 to right parts somewhere else so that they don't get overridden. I will actually give a glimpse of what I'm trying to say. Okay, so let's say at a certain point in between of the merge sort algorithm, we are having this as the left subpart, we are having this as the right subpart, okay? But this is the same ARR only, right? The ARR's 0, 1, 2 index is this, the 3, 4 index is this. And now we want the final ARR uh, array should look something like 1, 2, 3, 4, 5 with indexes 0, 1, 2, 3, 4. We want this, okay? So in that case, some overriding will happen while we will be merging, right? So we will be moving 3 from here to index 2, then 4 will go. So for those cases, we have to store this part. We have to create one more array, let's say left array, left ARR. We have to store this part in some extra array, which is some right ARR, and then we will use this left ARR and right ARR to populate this final ARR. Okay, so I will actually make you go through the algorithm. So we will be having a pointer at this left ARR. So this is the copied version now. This is not ARR now. This is the left ARR now. This is the right ARR now. Okay, and we will be having a pointer here, and the index will be here now 0 and 1. Why? Because this is a whole new ARR, right ARR, and the index will be 0, 1, 2. Good. Okay. Now, okay, so in this case, we have this as the I pointer, this as the J pointer, and I just want to tell you that just ignore whatever is there inside for now, because these elements will actually will not be 1 2 3 4 5. In the ARR it would be 1 2 4 3 5. Okay, good. Now we will be traversing it. ARRI and ARRJ, which is lesser? ARRI is lesser. So I will put ARRI here. I will also be having a K pointer here, which will actually see that how the ARR will be populated. So this point is populated, the K will move here. As we have populated it with I, so I will move to the next pointer now. Okay. Now I will check ARRI and ARRJ, which is lesser? ARRI is lesser. So I will put this 2 to this final ARR. I will move this K to here now, and I will move this I to here. Now ARRI and ARRJ, which is lesser? ARRJ is lesser. So I will put this 3 here. So do you see the overriding happening? And this way, if we are doing it with the same array, we will be losing 4 in such case. Okay. Now 3 is put, K will be pointing here, J will be incremented because the ARRJ is used. Good. Now among 4 and 5, ARRI and ARRJ, which is greater, which is lesser? 4 is lesser. So 4 will be put here, K will be incremented, I will be incremented. Now whenever one of the arrays goes out of bound, that it has ended, it has fully completed its loop, then whatever is remaining inside the other array will be populated inside the ARR. Okay, I hope you are able to understand this. Now the final ARR, what it looks like: 1 2 3 4 and 5. This is the final ARR. So this is the logic which we will be implementing here. We need to create the left ARR and right ARR. For that we need the size of the left ARR. Okay, so for that, what's the size of the left ARR? That would be mid minus left plus 1. Why do I say that? I say that because, okay, let's confirm that as well. So if you see here, this is left, this is mid. Okay, for this scenario, this whole scenario. Okay, when the indexes were 0, 1, 2, 3, 4. Okay, so left and this was mid. So what's the length of this array? 2 minus 0, mid minus L plus 1, 3. Okay, and what is the size of this? This will be, this is right. Okay, this 4 is right, so that will be around right minus mid. What is right? Right is 4. What is mid? Mid is 2. 4 minus 2 is 2 is size, and 3 is its size. So now int n2, which is the size of the right array, it will be right minus mid. Okay, till now it's fine. Now we will be computing int left arr is equals to new int, and with a size n1, int right arr is equals to new int with n2 size. We will also take the count as 0, and this is the inversion count only. So let's take this as inversion count. This is the inversion count only for this merge and count inversion. Whenever we are merging the left side and the left sorted and the right sorted array, then if we are getting anything which actually goes in between, okay, then we will add that. So in our case, as 3 goes here, right, which surpasses only single element. So this inversion count is for that. Okay, so in this step, I will be overriding the left ARR and the right ARR. For int I is equals to 0, I is less than n1 I plus plus. Left ARR of I is equals to, so the size of ARR, left ARR is n1, so I'm just going for that size only. So left ARR of I is equals to ARR of left plus I. Okay, let me just write that and then I will explain you what I have done. Same for the second array as well, that is the right array. Right array of j is equals to ARR of mid plus j plus 1. Okay, so what I have done now, if you see that I am populating left ARR I, which is the normal I index, with ARR of left plus I. And why I'm doing that? I am doing that, let me take this example. So for ARR, if I am taking this, for ARR, 3 and 5 was there, whose index was 3 and 4. Okay, the main ARR I am speaking. Okay, so for this, when I'm going to populate the left array, for it, what is the left array? The left array is 3. For it, what is the right array? The right array would be this one. Okay, okay, so when I'm doing that, what is my starting point for the ARR? That is 3, which is what? Which is left plus I, because I is 0 in this case. The starting point is left plus I. After that, I goes on based on the size, and we will just move forward if required. Okay, and for the right part, what is that? That is mid plus j plus 1. What is mid for this case? The mid for this case is 3 only. 3 plus 4 by 2 is mid, which is 3 only. So mid is 3, mid plus j plus 1. So when I am doing it here, what is the point of ARR? First point, that is 3 plus, what was initial j? 0 plus 1, 4. So index 4 is the starting point for the right, and that is what the starting point is. So as j goes on based on size of n2, we will move to the right if there are elements present. This is a shorter array which I have explained you, but if it would have more elements, then the more I and j will increase. Based on that, it will move forward. Okay, now with this, we have populated the left and right array, and I will highly recommend you to take some bigger examples, and then you will understand, okay, how the indexing, these values which I am taking, how they fit in. Okay, now is the logic for the actual merge happening. So we have int I is equals to 0, j is equals to 0 only, because they will be pointing to the initial elements of both sides. So if I take this case, this is I, as I have explained, and this is j, as I have explained. Okay, and what will be k? k will be left, because left is the initial element of ARR. Okay, you have to understand that left is the initial element of the actual ARR. Okay, now I will write the for loop while I is less than n1 and j is less than n2. So this is the standard merging of two sorted arrays into a single array, this algorithm. So we have to check that if our left ARR of I, is it lesser than or equal to left, sorry, right ARR of j? If that's the case, then I will actually make the ARR of k to left ARR of I, and I will increment the I and I will increment the k, because k will always be incremented because k is the final ARR, and I will be incremented because the left ARR of I is lesser. That is, I index actually traverses the left ARR, that is lesser, so I'm incrementing I for now, because from there we have got the minimum element. If that's not the case, it means definitely, so I'm using less than or equals to. If that's not the case, it means right ARR of j is definitely lesser, or left ARR of I is definitely greater than right ARR of j. Okay, here is the main thing which we need to understand. Here we will be incrementing the inversion count to what? That will be n1 minus I. I will explain you why I have done that, but before that, let me just write the code. ARR k is equals to ARR of, sorry, not ARR, right, ARR of j. We will do j plus plus because the smaller element has came from j side, and I will do k plus plus. Okay, so now why this n1 minus I? Let me tell you why. Okay, so in our case here, we had a 3, right? And at that point, what was I? What was I? I was here. Okay, at that point, I was here. So we checked, okay, 4 and 3, which is lesser? 3 is lesser. Okay, that is, it will move to this if condition, this else condition. Okay, now, as this is lesser, we need to see that how many elements it has to surpass. So how we will do that? N1, that is the size of this array, the left array. N1 was 3. What is I standing at? Which index it is standing at now? 2. So if we do n1 minus I, which is 3 minus 2, we will get the number of elements that j has to surpass and fit in at the right position of the sorted array. If we had some more elements here, let's say we have some 10, and I would be 2, same in this case, but n1 would be 4. So 4 minus 2, 2. So to fit in here as 3 from j, the 3 has to actually surpass 2 elements. So that's how n1 minus I is the count which we need to add to the inversion. Okay, now once that is done, okay, so now what we will be doing after this for loop has been while loop has been completed, we will be having one of the array which is completely exhausted, and either left array or right array, and one of the array which is having some more elements. So we need to add those elements to the final ARR, right? So for that, what we will be do, while I is less than n1, ARR of k is equals to left ARR of I and I plus plus and k plus plus. Okay, same thing goes for the right array as well. This I have managed for, so this one I have managed for the left array if there are some missing elements or there are some elements which are not exhausted, and for the right array, for j is less than n2, ARR of k is right ARR of j, and I will be doing j plus plus. K will always be incremented because it's the final array. Okay, now this thing is done, and after this big algorithm, we will be returning the inversion count. Okay, and when we do that, this actually completes the whole solution, and that was a big video, I understand, but you will get a lot of knowledge from it. Let's see if the things are passing or not. It's such a big code that I doubted that it will pass or not, but yeah, it's passing. Okay, so talking about the time complexity, it should be for the merge sort. Okay, because here we are exactly doing the merge sort thing. So the merge sort time complexity is big of n log n. So that is the time complexity as well for this problem. Going on to the space complexity, as we are using this left ARR and right ARR, in bits and pieces for the same single ARR only. So we are just creating uh, a space complexity of big O of n. That is, we are using an extra space of uh, size n only, because we are actually using the same array. We are cutting it into pieces, and those pieces we are taking a copy. So if we add all these copy of these pieces, that will be the same ARR only, and thus the space complexity we are taking an extra of big O of n. So that's all about the space and time complexity here. Will highly encourage you to just go through the video properly, understand bit by bit, try to code it out on your own and see if things work or not, and do submit it and see if all the test cases pass. Also, you can do a dry run with some more bigger examples so that you can understand the logic and the flow properly. Okay, so thanks a lot, guys. If you have any doubts, please put them in the comment section. I will be really happy to help, and that's all for today.